In this video, we're going to look at how we can use concavity of solutions to get the shape of graphs for autonomous equations, not just where they're heading. We've talked a lot so far about how we can tell the long-term behavior of solutions to autonomous equations by using stability and phase line graphs. But now I want to figure out more about the actual shape of these curves and what we can do to sort of figure that out. So when we're talking about shape of graphs, think back to Calc 1, we're normally talking about concavity. How we define concavity is defined by the second derivative of the solution curve. So let's see what we can learn from that. So with this scenario, we're looking at an autonomous equation. So we have our equation, dy dt equals some function f of y, and I want to use this to analyze the second derivative. So I want to look for d squared y dt squared. How can I interpret this? Well, the second derivative is the derivative of the first derivative. So derivative of dy dt, but I know what dy dt is. It's just f of y. And to show where we're heading next, y here is my solution curve, so y is a function of t. I want to differentiate this function, which is a composition f of y of t. That requires the chain rule. This will be f prime plugging in y of t, and then times y prime of t. But again, what is y prime? Y prime is just dy dt, which is just f. This is f prime of y times f of y. So our second derivative is computed as f prime of y times f of y, where f is the right-hand side of the autonomous equation. Well, what does that tell us? So this says that the solution curve, y of t, is concave up, which happens when the second derivative is positive, if f prime and f have the same sign at that value of y. If they're the same sign, they're either both positive or both negative. In both cases, the product is positive. And like everything else for this type of equation, it's only the y value that matters for what's happening here. So at a given y value, no matter where you are on the t-axis, it will be concave or concave respectively. Similarly, it's concave down if they have opposite signs. Now from this, where would I get inflection points? Well, your normal candidates are where the second derivative is 0, which in this case means that the product of f prime times f is 0, or one of those two things must be 0. However, we've seen that second one before. F of y being 0 means we have an equilibrium solution, which things aren't moving at all. There's no concavity there at all because things aren't moving up or down. So these ones don't matter. The only important thing to keep in mind here is we're going to see inflection points where f prime of y is 0. In particular, where f prime changes sign at a critical point. So to see how this impacts graph sketching for this, let's draw a random graph of some function f of y and see how that connects to where we're going to find equilibrium solutions and inflection points and how that affects our process. We have some axes. They're going to be axes for y versus f of y. I'm going to draw a random graph here. Here's my graph of f of y. So let's first find where I have equilibrium solutions. Those are going to be where f of y is 0. So I can mark all those on here. They are the places where the graph crosses the y axis, which is the horizontal axis for this problem. So our points are here, 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 and here. So we have 4 different equilibrium solutions here. Where are we going to find inflection points? Well, those are going to happen when f prime is 0, which are going to be at the peaks or valleys of these curves. So we'll have one here, and one here. Now, if you'll notice, we have one between each pair of equilibrium solutions. That might seem like a shocker, but if you think back to some stuff we did in Calc 1, it's actually not that surprising. What do we have? Well, we have a function f that has 2 zeros at 2 points here. So f of a and f of b is 0. This being a and b, and it's differential between the 2 points, which means by Rolle's theorem, there has to be some point in between where f prime is 0. That's exactly our inflection point up here. Break this down a little bit further. If we look in the region here, so between this first orange dot and the green dot, what is f? Well, f here is positive because I'm above the axis. So f is positive, and what is f prime? F prime is also positive because my graph is increasing up to that max value. They have the same sign, therefore the graph will be concave up for these values of y. If we look on the other side of that green dotted line, we have f is still positive, the graph is still above the y-axis, but f prime is now negative, so it's going to be concave down in here. You can keep this process going. Now, if I flip this now into a phase line to sketch out some graphs, we can see what they actually look like in the actual graph part of this. So flipping this on its edge, I'll put 0 here as a mark. We have 4 equilibrium solutions, 2 that are positive and 2 that are negative. So 1 and 2 that are positive here. 1 is barely negative, 1 is much more negative. I can draw my arrows in here. we see that below the lowest equilibrium solution, f is negative, so the function is decreasing there. In between those two there, a negative means it's positive. We have negative, negative, and positive. So now I can draw my solution curves with these things drawn out. Here are my axes here. Now again, this here is a ty graph. I'm gonna zoom in a little bit on it. And we can draw in our equilibrium solutions as straight lines. And for the sake of this, I'm gonna add in the green dots as well. There was a green dot in between these two, just positive, and in between these two, and I will add these dotted lines across here in the middle. These are not solutions, they are just markers for where these green values are. Now, what did we see in our analysis above? We saw that the graph is going to be concave up in this region and concave down in this one. And we also know because the arrow points up, the solution has to be increasing, which all this fits together to make sense what we're going to draw on this graph. Because if we're below that green line, we have to be concave up. So concave up in here. We hit that green line. That's our inflection point. Now we're concave down, and we flatten out this way. Now, knowing that we had to approach the bottom line going to minus infinity, and the top line going to plus infinity, means we had to be concave up below and then concave down above. That is always the case if you're going to get this proper asymptotic behavior. We could see for the other ones, the exact same process happens. And you get your graph to look like this. So every one of these regions has an inflection point in it. The graph will always be concave up on the bottom side of that line, wherever that may be on the left or the right side. It'll be concave down on the top side of that line. And it basically works because if the graph is going away from the y=0 line, it's going to be concave up. And if it's going towards, it's going to be concave down. In any case, that's how you could then find these inflection points by looking for the values where the derivative of the function on the right-hand side of the equation is 0. That will tell you where the inflection points are, and you can use them to help sketch out the graphs. Now in the future, you're not really going to be finding these actual values that often. You just have to know that there's going to be one in between every single pair of equilibrium solutions. So you can use that to your advantage when trying to sketch out these solution curves. You know, they have to flip over at some point from concave up to concave down, or vice versa. So that's how you can use concavity analysis or shape analysis to get more information on the actual structure and shape of solutions for autonomous equations.